Welcome to today's session. In this video, we'll tackle problem number 218, the Skyline problem. This is a fascinating computational geometry challenge that involves determining the skyline formed by a collection of buildings. We'll explore the problem, break it down step by step, and discuss various approaches to solve it. Let's dive in. The skyline problem involves determining the outline of a city's skyline when given a collection of rectangular buildings in a two-dimensional plane. Each building is defined by three values: the left x-coordinate of its starting edge, the right x-coordinate of its ending edge, and its height. These buildings may overlap, and our task is to calculate the key points where the skyline changes height. These key points are represented as x, y pairs, where x is the position along the x-axis, and y is the new height of the skyline at that position. The output must be sorted by the x-coordinate, and we need to ensure there are no redundant points. For example, if two consecutive points have the same height, the second point should be omitted. The output of the problem is a list of these key points, x, y, that describe the skyline. Let's look at an example. Suppose we have three buildings defined as 2, 9, 10, 3, 7, 15, 5, 12, 12. The first building starts at x equals 2, ends at x equals 9, and has a height of 10. The second building starts at x equals 3, ends at x equals 7, and has a taller height of 15, overlapping the first. The third building spans from x equals 5 to x equals 12 with a height of 12, overlapping both earlier buildings. The resulting skyline changes height at specific x-coordinates, forming the output 2, 10, 3, 15, 7, 12, 12, 0. This means the skyline starts at a height of 10 at x equals 2, peaks at 15 at x equals 3, drops to 12 at x equals 7, and finally returns to 0 at x equals 12. Breaking this down further, the skyline begins at x equals 2 with a height of 10, reflecting the first building. At x equals 3, the taller second building increases the height to 15. Then, at x equals 7, the height decreases to 12 as the second building ends, leaving only the third building. Finally, at x equals 12, the skyline drops back to 0, marking the end of all buildings. Let's consider another example with two buildings, 0, 2, 3, 2, 5, 3. Here, the first building spans from x equals 0 to x equals 2 with a height of 3, and the second building continues with the same height from x equals 2 to x equals 5. Since the height remains constant, the skyline simply starts at x equals 0 with height 3 and drops to 0 at x equals 5, yielding the output 0, 3, 5, 0. Now, let's look at a more complex example, 1, 5, 11, 2, 6, 7, 3, 9, 13. These buildings overlap significantly, creating a skyline that changes height at multiple points. The first building starts at x equals 1 with a height of 11. At x equals 3, the third building, which is taller, increases the height to 13. Finally, at x equals 9, the skyline returns to a height of 0, as all buildings end. This results in the key points 1, 11, 3, 13, 9, 0. When solving this problem, there are several constraints and edge cases to keep in mind. The input list can contain up to 10,000 buildings, and their coordinates and heights must fall within specified bounds. Additionally, the output must be sorted by x-coordinates, and redundant points, such as consecutive ones with the same height, must be removed. Consider cases like non-overlapping buildings, multiple buildings with the same height, or even an empty input list, all of which should be handled correctly to ensure a valid skyline representation. To start, let's consider the brute force approach. The intuition here is to construct the skyline step by step by iterating through each building and determining its contribution to the final result. For every building, we analyze its impact on the skyline between its left and right boundaries. The key observation is that the height of the skyline at any point is dictated by the tallest building covering that point. The process involves dividing the x-axis into small intervals based on the building boundaries, calculating the maximum height within each interval, and then merging these intervals to form the complete skyline. While this method is straightforward to implement, it has significant inefficiencies. Specifically, the time complexity can reach n squared, in the worst case due to repeated comparisons, making it unsuitable for large inputs. Although simple, its quadratic complexity is a major trade-off to consider. Now, let's explore the optimized divide and conquer approach, which draws inspiration from the merge sort algorithm. The key idea is to divide the buildings into smaller subsets, compute the skyline for each subset, and then merge these partial skylines into a single result. A critical observation here is that combining two partial skylines is similar to merging two sorted arrays, and as we merge, we track the height changes to maintain the correct skyline. This approach involves recursively dividing the list of buildings into two halves, solving the problem for each half, and then merging the results using a two-pointer technique. The time complexity of this method is O(n) log n, due to the recursive division and linear merging, and it uses O(n) space for temporary storage during the merge. While this approach offers a significant boost in efficiency compared to brute force, it is slightly more complex to implement, which is a trade-off to keep in mind. Next, we have the optimized sweepline approach with a priority queue, which is the most efficient method for this problem. The intuition here is to use the sweepline algorithm combined with a max heap to dynamically track the maximum height as we process events sequentially from left to right. The key observation is that the critical points of the skyline occur at the left or right edges of buildings, where the height of the skyline changes. The process involves representing all building edges as events, sorting them, and using a max heap to manage active building heights. As we process each event, we update the heap and check if the maximum height has changed. If it has, we record the new height in the result. This method achieves a time complexity of O(n) log n due to sorting and heap operations, with an O(n) space requirement for the heap. Its ability to efficiently handle height changes makes it highly effective for large inputs. The sweepline approach with a priority queue stands out as the most efficient strategy for solving the skyline problem. This method is particularly advantageous for large inputs because it processes events in sorted order and dynamically updates the skyline using a max heap. These features make it scalable and well-suited for competitive programming. Additionally, it avoids the recursive overhead inherent in the divide-and-conquer approach and the inefficiencies of the brute force method. However, the trade-offs include a slightly higher implementation complexity and the need for additional data structures like a max heap, which can be challenging for beginners. Despite these challenges, the combination of scalability, efficiency, and practicality makes this approach the preferred solution. In conclusion, the sweepline algorithm with a priority queue emerges as the optimal solution for the skyline problem. Its ability to efficiently process events, handle large inputs, and dynamically update the skyline makes it the best choice among the approaches discussed. While it does require careful implementation and an understanding of complex data structures, its scalability and performance make it a clear winner for solving this problem effectively. The skyline problem asks us to determine the silhouette formed by a collection of buildings when viewed from a distance. Each building is represented as a triplet: left, right, height, where left is the x-coordinate of the building's left edge, right is the x-coordinate of its right edge, and height is the vertical height of the building. Our task is to compute the skyline, which is a series of key points, x, height, that define the outline of the buildings. These key points represent the critical x-coordinates where the height of the skyline changes, allowing us to capture the overall shape of the building's combined profile while ignoring unnecessary details like flat sections at the same height. To solve this problem, we start by defining the input and output. The input is a list of buildings, each described by left, right, height, and the output is a list of key points, x, height, that represent the skyline. The first step in the algorithm is to extract events from the buildings. For each building, we create two events: a start event at the x-coordinate of the left edge, with the building's height, and an end event at the x-coordinate of the right edge, also with the building's height. To differentiate between start and end events, we store start events as left, height. Using a negative height ensures that start events are prioritized over end events when processing. End events are stored as right, height. This approach allows us to distinguish between the two types of events and ensures that taller buildings are processed first, which is crucial for correctly determining the skyline. Once the events are extracted, we sort them by x-coordinate. If two events occur at the same x-coordinate, we prioritize start events over end events. Additionally, if two start or end events coincide, we process taller buildings first. This sorting ensures that we handle overlapping buildings accurately and avoid introducing incorrect key points. After sorting, we begin processing the events using a max heap, which helps us track the heights of active buildings efficiently. The heap is initialized with a height of 0 to represent the ground level, and we maintain an empty list called result to store the key points of the skyline. As we iterate through the sorted events, we check whether the event is a start or end event. For a start event, we add the building's height to the heap. For an end event, we remove the building's height from the heap. After updating the heap, we determine the maximum height. If this maximum height changes, it indicates a transition in the skyline at the current x coordinate, so we add a new key point, x, max_height, to the result. After processing all the events, the final step is to return the result list containing the computed key points of the skyline. This list represents the outline of the buildings as seen from a distance. The algorithm relies on several key insights to ensure correctness and efficiency. The max heap is critical for dynamically tracking the tallest building at any given x coordinate, allowing us to efficiently handle overlapping buildings. Sorting the events by x coordinate and resolving ties intelligently ensures that the buildings are processed in the correct order, avoiding discontinuities in the skyline. Finally, by adding a key point only when the maximum height changes, we minimize redundant points in the output, producing a concise and accurate representation of the skyline. The algorithm uses three main data structures. First, the max heap, which stores the heights of active buildings and allows efficient retrieval of the tallest height at any x coordinate. This is essential for dynamically tracking height transitions during event processing. Second, the result list, which stores the key points, x, height, that define the skyline. This list directly represents the desired output and is updated only when a height transition occurs. Third, the event list, which contains all the start and end events, sorted by x coordinate and height. Sorting ensures that the events are processed in the correct order, enabling accurate handling of overlapping buildings and transitions. Together, these data structures provide the foundation for efficiently computing the skyline. The algorithm has a time complexity of O, n log n. Sorting the events requires O, n log n, and processing the events involves heap operations, which also take O, n log n, in total. The space complexity is O, n, as we need to store the events and the active building heights in the heap. To ensure the algorithm handles all scenarios correctly, we consider several edge cases. For a single building, the output consists of two key points, one marking the start of the building's height and another marking the return to ground level. For multiple non-overlapping buildings, the key points alternate between the start and end of each building. For fully overlapping buildings, the skyline reflects only the tallest building, with key points marking its start and end. These cases demonstrate the algorithm's ability to handle diverse inputs while maintaining correctness and efficiency. To solve the skyline problem, we start by importing the heap module to utilize a heap for efficient processing. Inside the getSkyline method, the first step is to extract all the critical points from the building's array. For each building, we identify the left and right edges and note their heights. We store these as tuples in the critical_points list, where the left edge is represented with a negative height. This negative value helps us use a max heap later on since Python's heap is a min heap by default. For the right edge, we use a positive height to indicate the building's end. After gathering all the critical points, we sort them primarily by their x coordinates. If 2 points have the same x coordinate, we sort by height to ensure the order is consistent. Next, we prepare to process these points. We initialize an empty result list to store the skyline's key points and set up a live_buildings heap to track the active building's heights. Initially, this heap contains a dummy building with height 0 and an end position of infinity, ensuring that even when no buildings are active, the skyline is properly calculated. Then, using a loop, we process each critical point to dynamically construct the skyline. Within the loop, we handle two cases for each critical point. If the height is negative, it indicates the start of a building, so we push it onto the heap. This effectively adds the building to our list of active structures. Conversely, if the height is positive, it signifies the end of a building. Here, we would typically remove the building from the heap, however, this part is simplified for clarity in the current code. After updating the heap, we extract the maximum height from the top of the heap, which represents the tallest active building at the current x coordinate. If this maximum height differs from the last recorded height in the result list, it means the skyline shape has changed, and we append a new key point to the result. This ensures that the skyline updates only when there's a visible change in height. Finally, once all critical points are processed, the result list contains the complete set of key points defining the skyline, and we return it as the output. To solve the skyline problem in Java, we start by defining the main method, getSkyline, which takes an array of buildings as input. The first step involves identifying the critical points, which are the start and end edges of each building. For the start edge, we use a negative height to differentiate it from the end edge, which has a positive height. This distinction helps us determine when a building begins or ends as we process the skyline. Next, we sort these critical points. The sorting is based primarily on the x-coordinate, ensuring we process points from left to right. If 2 points share the same x-coordinate, we further sort by height to handle overlapping buildings correctly. After sorting, we prepare to construct the skyline by initializing a max heap with a ground level of 0. This heap will help us efficiently track the highest building at any given point on the x-axis. Now, we iterate through the sorted critical points. For each point, we check its height. A negative height indicates the start of a building, so we add its absolute value to the max heap. A positive height, on the other hand, signifies the end of a building, so we remove that height from the heap. The max heap then gives us the current maximum height of the skyline. If this maximum height changes compared to the previous maximum, it means a new key point in the skyline has been identified. We record this key point as a pair of the x-coordinate and the new height. Finally, the list of key points accumulated in the result variable represents the skyline and is returned as the output. To solve the skyline problem, we begin with a straightforward example consisting of a single building defined by the input buildings equals 2, 9, 10. This building starts at position 2, ends at position 9, and has a height of 10. The first step is to extract the critical points, which represent where the building starts and ends. For the start of the building, we add the point 2, minus 10, where the negative height indicates the beginning of the building. For the end of the building, we add the point 9, 10, where the positive height signifies the end of the building. After extracting these points, the result is critical underscore points equals 2, minus 10, 9, 10. Next, we sort these critical points by their x-coordinates and, if necessary, by height. In this case, the points are already in order, so the sorted result remains 2, minus 10, 9, 10. Now that we have the sorted critical points, we process them to construct the skyline. We initialize two structures, live_buildings, which keeps track of active buildings using a max heap starting with 0, inf, and result, which stores the skyline points as we process. For the first critical point, 2, minus 10, we add minus 10, 2, to live_buildings, representing the building's height and its end position. The current maximum height is dash, minus 10 equals 10, so we add 2, 10, to the skyline result. Next, we process 9, 10, which marks the end of the building. We remove 10, 2, from live_buildings, leaving the ground level as the maximum height, which is 0. Therefore, we add 9, 0, to the result. The final skyline for this example is 2, 10, 9, 0. Let's move to a more complex example with overlapping buildings. Here, the input is buildings equals 2, 5, 10, 3, 7, 15. The first step is to extract the critical points for both buildings. For 2, 5, 10, we add 2, minus 10, for the start and 5, 10, for the end. Similarly, 4, 3, 7, 15, we add 3, minus 15, for the start and 7, 15, for the end. This gives us critical underscore points equals 2, minus 10, 5, 10, 3, minus 15, 7, 15. Next, we sort these points. Sorting by x-coordinates and heights, we get 2, minus 10, 3, minus 15, 5, 10, 7, 15. This ordering ensures we process the critical points in the correct sequence to calculate the skyline accurately. With the sorted critical points, we can now compute the skyline. We initialize live_buildings equals 0, inf, and an empty result. Starting with 2, minus 10, we add minus 10, 2, to the heap. The maximum height becomes 10, so we record 2, 10, in the result. For 3, minus 15, we add minus 15, 3, to the heap, making the maximum height 15. This height change is recorded with 3, 15. When processing 5, 10, we remove minus 10, 2, from the heap, but the maximum height remains unchanged at 15, so no new point is added. Finally, with 7, 15, we remove -15, 3 from the heap, reducing the maximum height to 0. This drop is captured with 7, 0. The resulting skyline is 2, 10, 3, 15, 7, 0, which reflects the overlap between the two buildings. Now consider an example with non-overlapping buildings, where the input is buildings equals 2, 4, 10, 6, 8, 15. As before, we start by extracting critical points. For the first building, 2, 4, 10, we add 2 minus 10 for the start and 4, 10 for the end. For the second building, 6, 8, 15, we add 6 minus 15 for the start and 8, 15 for the end. This results in critical underscore points equals 2 minus 10, 4, 10, 6 minus 15, 8, 15. Sorting these points by x-coordinates and heights gives the same order, 2 minus 10, 4, 10, 6 minus 15, 8, 15. The non-overlapping nature of the buildings ensures that the skyline will contain distinct peaks for each building. With the sorted critical points, we determine the skyline step by step. Starting with 2 minus 10, we add minus 10, 2 to live underscore buildings. The maximum height becomes 10, so we add 2, 10 to the result. 4, 4, 10, we remove minus 10, 2 from the heap, reducing the maximum height to 0. This drop is recorded with 4, 0. Next, 4, 6, minus 15, we add minus 15, 6 to the heap. The maximum height becomes 15, so we add 6, 15 to the result. Finally, with 8, 15, we remove minus 15, 6 from the heap, bringing the height back to 0. This change is captured with 8, 0. The final skyline is 2, 10, 4, 0, 6, 15, 8, 0, which clearly shows the distinct peaks of the two non-overlapping buildings. To analyze the time complexity of this solution, we start by breaking the process into distinct steps. First, we extract critical points from the buildings. For each building, we identify its start and end points and add them to the critical points list. Since there are n buildings, this step takes n time. Next, we sort these critical points based on their x-coordinates and height. The total number of points is 2n, so sorting them takes 2n asterisk log 2n, which simplifies to n asterisk log n. After sorting, we process each critical point to update the max heap that keeps track of live buildings. Adding or removing elements in a heap of size k takes log k time, and in the worst case, the heap could contain all n buildings, resulting in log n per operation. Since there are 2n critical points to process, this step takes 2n asterisk log n, which simplifies to n asterisk log n. After processing the critical points, we update the result list to store the key points of the skyline. Each critical point contributes at most one operation to the result, so appending these points takes 2n, which simplifies to n. Combining all these steps, the overall time complexity becomes n for extracting critical points, n asterisk log n for sorting, n asterisk log n for processing critical points, and n for updating the result. Dominated by the sorting and heap operations, the final time complexity is n asterisk log n. Moving on to space complexity, the critical points list requires storage for 2n points, which is n. The max heap for live buildings, in the worst case, holds all n buildings, also requiring n space. Additionally, the result list that stores the skyline key points requires space proportional to the number of key points, which is at most n. Finally, the sorting step involves auxiliary space for the sorting algorithm, which also takes n in the worst case. Summing these components, the overall space complexity becomes n for the critical points, n for the heap, n for the result list, and n for auxiliary space, resulting in a total space complexity of n. This efficiency makes the solution suitable for handling large inputs, as both time and space complexities are manageable. To put these results into perspective, we can compare the current optimized solution to a brute force approach. In a naive method, we would iterate through the entire range of x-coordinates and compute the height for each x by iterating through all buildings. This results in a time complexity of L asterisk n, where L is the range of x-coordinates, which can be very large. The space complexity in this case would also be L, as we store the height map for the entire range. The optimized solution, however, reduces the time complexity significantly to O(n*log n by focusing only on critical points and leveraging a heap for efficient processing. The space complexity is also reduced to O(n), as it avoids storing unnecessary data like the height map for every x-coordinate. The efficiency of the solution can be further understood by analyzing the best, average, and worst cases. In the best case, where buildings have minimal overlap, the heap remains small, and the overall complexity is dominated by the sorting step, which is O(n*log n). In the average case, with moderate overlap, the heap grows and shrinks dynamically, but the time complexity remains O(n*log n). Finally, in the worst case, where all buildings overlap, the heap size reaches its maximum of O(n), but even then, the processing step still adheres to O(n*log n). The use of sorting and heap operations ensures that the most expensive steps are logarithmic, making the solution asymptotically optimal. This approach is a significant improvement over the brute force method, especially for large-scale problems where efficiency is critical. When solving the Skyline problem, there are several common mistakes to watch out for. First, overlooking how to handle overlapping buildings can lead to incorrect results. For instance, if one building partially overlaps another but is taller, its height should dominate in the skyline. Failing to properly manage these overlaps could result in inaccurate height calculations. Another issue is using inefficient data structures. For example, relying on a simple list instead of a priority queue can significantly slow down your solution, especially with larger inputs, leading to suboptimal runtimes like O(n²) or worse. Then there's the issue of off-by-one errors, particularly when managing the start and end points of buildings. Missteps here, such as including the end coordinate of a building when it shouldn't be part of the skyline, can produce duplicate points. Lastly, it's easy to overlook edge cases. Scenarios like buildings with zero width, those starting and ending at the same point, or even just having one building in the input need special care. Ignoring these can result in unexpected behavior in your solution. Another mistake to avoid is generating redundant points in the skyline output. These occur when the height doesn't actually change, and a correct solution should ensure that each point in the skyline represents a meaningful height difference. Now, when preparing for interviews, it's important to note a few things. This problem is a classic example of a sweepline algorithm, a key pattern that can be applied to many problems involving intervals or events. Optimizing for both clarity and performance is essential. A well-explained O(n*log n solution is often preferred by interviewers over a rushed or buggy O(n)(1). To break down the problem effectively, you should discuss how you process start and end points, often referred to as events, and explain how a priority queue or similar structure is used to maintain the active set of buildings. Communication is also key. Be sure to articulate how you handle edge cases and discuss trade-offs between different approaches, such as using divide and conquer versus the sweepline method. The skyline problem is closely related to several other problems that can deepen your understanding of interval handling. For example, LeetCode 57, Insert Interval, introduces interval merging techniques, while LeetCode 732, My Calendar 3, also uses the sweepline method with event handling. Additionally, LeetCode 253, Meeting Rooms 2, teaches how to use a priority queue to manage interval overlaps. Now, let's look at alternative approaches to solving this problem. A brute force method involves iterating through all buildings and manually updating the skyline. While simple to implement, its O(n²) complexity makes it unsuitable for large inputs. A more sophisticated approach is divide and conquer. Here, you recursively divide the buildings into two halves, compute the skyline for each half, and merge the results. This method achieves O(n*log n complexity and is elegant and efficient, though merging the results can be challenging to implement correctly. The most commonly used method for solving the skyline problem is the sweepline algorithm combined with a priority queue. This approach involves sweeping through sorted events, which represent the start and end points of buildings, while maintaining the active set of buildings in a priority queue. With a time complexity of O(n*log n, it offers a good balance between efficiency and clarity. However, it does require careful handling of edge cases to ensure correctness. These might include scenarios like overlapping buildings, buildings with zero width, or ensuring the skyline output doesn't include redundant points. This method is widely favored because it's both performant and aligns well with the problem's requirements, making it an excellent choice for interviews or practical applications. Great job! We learned about the Skyline problem and discussed its brute force approach. Remember, tackling such problems improves your algorithmic thinking and prepares you for more advanced challenges. Thanks for watching, and don't forget to like, subscribe, and share. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!